Hello, let's start with a powerful message. All things are difficult before they are easy. But that's enough philosophical talk. Let's move on to the learning. Here we have a casual t-shirt that can be worn by normal people. So what is the point of this video, you may ask, and what will I talk about? If you guessed that we are going to explore the basics of the normal distribution, you guessed right. Let's dive in. You may already know how a histogram looks. However, collecting tons of data to estimate probabilities can be expensive and time-consuming. It is also not clear what to do with gaps in data, if the bins are too wide or narrow, since histograms are sensitive to bin size. Note, when I'm talking about bins, these are not trash bins. These are just a way of keeping the data in a very tidy way. Now let's jump into this very funny, nice looking diagram here. So the normal distribution is an example of a continuous distribution, and probability distributions can be discrete or continuous. As you can see, the graph creates a bell-shaped curve. Let's discuss some features and consider the normal distribution as well as what it represents in terms of a certain context. So let's take the heights of certain individuals or people in a sample population or a population overall. As you can see from this bell-shaped curve, it's symmetrical about the mean or average value. And the average height of a certain individual is where that maximum value would occur. And this is demonstrated by the peak over here. Lots of people would be in that height range. So let's take the mean in our example as 170 centimeters, and we will be using this for later on purposes. It is very rare, however, to see someone who is super short and in this end of the distribution or graph, as well as it is very hard to see someone who is super tall, and this is all seen by the tail ends of this distribution. The width of the distribution, which is shown like this, is defined by the standard deviation. This is useful since about probably 95% of data values or measurements lie between plus or minus 2 standard deviations around the mean. So let's take the mean height to be 170 centimeters as we said, and the standard deviation, let's say, is 1.5. Now, people's heights would lie between 167 centimeters and 173 centimeters. So this would probably be 167. The mean runs at 170 over here. And we've then got 173 centimeters, and 95% of values will fall within that range. So to find the probability of, let's say, a person's height falling under 155 centimeters to 165 centimeters, for example, it's basically to calculate it, the area under the curve. So we taught the mean here is 170 centimeters. 155 could be somewhere around here in the tail end, because we did that 2 standard deviations around the mean is 167 and 173. So let's say 155 is around here and 165 is here. So we're calculating between here and here, like just one small segment. It might be better with an illustration, but hopefully it gives a clear or decent enough picture. So to calculate the area under the curve, it can be done through calculus, through integration. However, nowadays we have a computer, and the computer can essentially do this for us. If you want to know probabilities though of someone who is exactly 163 centimeters, for example, let's say, it will come to 0, because continuous distributions are infinitely precise and they wouldn't very well be applicable in that kind of context. It measures it, as this graph is continuous, it measures values that are of a certain range. Hopefully this helps.